Hey everyone, so in this next video we're going to talk about integrals. In particular, we're going to talk about how to find the integrals of polynomial functions, of trig functions, uh, the definite versus indefinite integrals, and I'll talk a little bit about the complex integral application, though I'm not going to go into detail now. I'm going to save that for another video. So what are the types of equations that we need to do integrals for? As I mentioned before, we have to do it for polynomials and trig functions. Just a quick little refresher. There is a chance you might have to do it for other equations. However, I would just kind of bite the bullet on those because they are extremely rare and not really worth spending too much time focusing on that. So how do you find the integrals of polynomials? Well, for the most part, as I mentioned before, the integrals are the exact opposites of derivatives. So it actually makes sense that the steps are the exact opposite. So remember, the steps to do derivatives was we multiplied the coefficient by the exponent and then subtracted 1. What we're going to do next is add 1 to the exponent and then divide the coefficient. So I'm doing the opposite of each step and in reverse order. So here we have an equation. I take the integral of 8x cubed minus 9x squared. Again, I write it with dx to show what exactly is being integrated, what variable. I'm going to add 1 to the exponent of 3 to get 4, and I'm going to divide the 8 by 3 plus 1, which is 4. I do the same thing for the 9. I add 1 to the exponent to get 3, divide the 9 by 3, and I get 2x to the 4 minus 3x cubed plus c. Well, where did the c come from? What's going on? Well, this is actually because of the fact that, as we mentioned in derivatives, when we take the derivative of a constant term, that term goes to 0. So if we actually work our way backwards and we take the integral, we don't actually know if there was or wasn't any sort of constant term there. We would need a little bit more information. So a lot of times in a question, they will tell you initial values. For example, if this equation is supposed to represent something like the position of a particle, then what C would represent is what the initial position was in the beginning. And that's it. Now, for the most part, there are ways to figure out what C is, but this is kind of like a little placeholder to say that there's something there. We don't know what that constant term is without a little bit more information. You'll see some examples in problems that you do of how to figure out what that is. Now let's see a slightly different case. So here we have this 3x squared minus 2x plus 4. Again, we do the same thing. We add 1 to each of these exponents and divide the coefficient. So 2 plus 1 is 3. 3 divided by 3 is 1. So this becomes x cubed. We add 1 to this exponent to get 2. 2 divided by 2 is 1. So we get x squared. There is no exponent because this is a constant. There is no exponent, so it's just 0. Add 1 to it, divide 4 by the 1, and we get 4x. So it's just adding on an x, and we get plus c. Now, one thing that you can do to check to make sure that your integral is done correctly is just take the derivative of your final answer, and you should end up with this. Multiply the coefficient, we get 3x squared minus 2x plus 4. And there we go. Because this, a lot of times people will call integrals antiderivatives because they're the exact opposite of a derivative. Now, what about trig functions? Again, the steps are the exact opposite. This time, not in opposite order though, but we're going to divide the coefficient by whatever the number is in front of the x inside the sign term. And then again, we replace the sign or replace the trig function with whatever the integral form is. In this case, if we had this, so we would take the 4 divided by 2, okay, makes sense. But this time the sign gets replaced with negative cosine. Again, the sign kind of makes things a little bit weird. So putting this all together, the integral of 4 sine 2x with respect to x will end up being, well, 4 divided by 2, that inner part gets us 2. We replace the sign with negative cosine, so it all comes out to negative 2 cosine 2x. Again, you don't need to memorize these. These are on the reference table, but it's important it is useful to remember it. So sine, the integral of sine is negative cosine, and the integral of cosine is sine. So again, we're replacing sine with cosine. The only thing is you just have to be careful with where the negative goes. What are some applications? I mentioned this before about this idea about definite and indefinite integrals. Basically, what we've been doing before was doing the indefinite integral. We didn't really take into consideration anything about bounds or intervals. We just went from one equation and we got a new equation. So perfect example of this is if I gave you an equation that represented velocity and I wanted an equation that represented the position, you would do an indefinite integral. What about the definite integral that we talked about? Well, as I mentioned, you would need to know what interval they're talking about. What are the values of x that we're supposed to be considering? And these numbers are going to be acting as what's called your bounds. The way we represent those bounds is by placing them above and below that little squiggle sign. So for example, if we were doing the integral between x equals 1 and x equals 5, I would make my little squiggle and then I'd put a 1 at the low end and a 5 at the upper end. And then I would write everything else the way I would do it. Now, how do we actually incorporate this? Well, once we take the integral like we did last time, we get to the same step. And then what we do is on the right-hand side, we draw a little line. And then again, we write 1 and 5. Now what we have to do is what's called evaluating the bounds. What that means is we plug in these numbers, 1 and 5, into this equation for x, and then we subtract the two terms. This is essentially doing final minus initial. So here, our final number is 5, so I take the equation, I plug a 5 in for the x in these two terms, then I do minus, and then I plug in a 1 because of my initial term. This ends up getting me the equation 875 plus c minus -1 plus c. What about the c? Well, guess what? It cancels out because we end up having the constant term isn't affected. So it ends up being c minus c, which gets us 876. So again, we end up with a single numerical number. So we end up getting just a number. So you don't need, a lot of times you're going to be dealing with definite integrals. So you kind of don't need to worry about c. And this is why I said, for the most part, it's really there as a placeholder because a lot of times it gets dropped out. And usually they kind of have this scenario be where the initial values tend to be 0 anyway. So, just make your life easy. Now, what about the complex integrals I was talking about? Well, like I said, this is a very specific scenario. You should be aware of this, but it's not completely necessary to focus on it too much because, like I said, it only comes up in one scenario. But it's useful for those, moving on to later parts of physics and calculus to be aware of this. So what's important to remember is when you do the integral, the term dx tells me what exactly is being considered a variable and what's being considered constant, just like I said with the derivative part. Let's say we had a scenario like this. We took the integral of the function 5b and we're doing it with respect to x. So because x is my variable, I would look at my function and say, where is the x term? Because I don't have an x term, it would mean that the 5b is being considered as a constant term. So the b actually doesn't mean anything. I don't have to worry about it. I'm not going to add an exponent to b. It's nothing. So if I consider it a constant, it will end up being 5dx, just like how the equation would end up being 5x if I was just taking the integral of 5 with respect to x. Now, uh, what if the b actually wasn't a constant? What if b was dependent on x, or there was a relationship between b and x that I had to understand, I had to find? Well, in those cases, you have to do some extra work. What you have to do is rework the equation so that the terms are in the proper variables. A perfect example of this, and this is actually the scenario that gets used for it, when you do the rotational inertia, the equation is written as this: the integral of r squared dm. And you might be thinking, well, m is mass. Um, this equation doesn't have m in it, so this must be a constant. Yes and no. It actually isn't, because as our radius changes, so does the mass. So in the next video, in one of the later videos, actually, not the next one, in the later video, I will show you how to do this. I'll go into more detail. Just be aware, extremely rare and is only brought up in this scenario. So you don't have to worry about it too much. That's it. Hopefully you know a little bit more about integrals. If you have any questions, feel free to let me know. Otherwise, good luck and